formula for the Z2 invariant in the three-dimensional topological insulator, which was this somewhat complicated but interesting integral over the non-abelian Berry phase of the bulk. I want to make that a bit more physical by trying to answer the question, what is quantized in a topological insulator the way that the Hall effect is quantized in the quantum Hall effect? And the answer is especially interesting for the 3D topological insulator, so I'm going to focus on that. And let me give a little bit of historical background, how people, more or less by accident, were almost thinking about the 3D topological insulator long before the present day. And it turns out that this is maybe a way to lead into another question. So aside from the question of what's quantized in topological insulators, you can ask, well, one of the definitions I gave so far was that the 3D topological insulator is something that has gapless surfaces with an odd number of Dirac cones. If it has Dirac cones, that means it's kind of like graphene. And you've already heard that graphene is great, so how does this surface, which also has massless fermions, behave differently from the graphene surface? So I'm going to focus not on repeating stuff about Dirac fermions, but on what's new when you have an odd number. Turns out that a surprising number of things change. More than just a factor of 2, that is. Okay, so an interesting thing that particle physicists noticed when they were thinking about a particle called the axion, that we still haven't found, was the following. We know that when we go into a solid, we change Maxwell's equations a little bit. So I'm mostly going to use the blackboard as usual. I thought I'd flash up a few slides for kind of motivation and to get the equations out there, and then I will get back to the blackboard. So in addition to changing the dielectric constant, the magnetic permeability, you can imagine a magnetoelectric material where you have some bilinear term in the electric and magnetic fields. And what this kind of response means, this was studied going back to the 1950s, that if you have some crystals with low symmetry, basically crystals that break both inversion and time reversal, then you tend to create terms like E dot B, E cross B, etc. in the effective Lagrangian. These terms just mean that applying a magnetic field produces an electric moment and vice versa. So these would be called magnetoelectric materials. To be precise, linear magnetoelectric materials. The reason why you have to break inversion and time reversal is that magnetic fields are even under inversion and odd under time reversal. Electric fields are odd under inversion because there's a spatial direction, but even under time reversal. You can kind of understand those symmetries just by staring at the Lorentz force law, E plus V cross B. So a term like this, superficially, is both time reversal breaking and inversion breaking. But there's something special about E dot B compared to E cross B or the others, for example, and this is the first thing I'm going to show on the blackboard, which is that this is a total derivative of something interesting. So if I took E cross B, I don't know of any sense in which E cross B is topological or a surface term. It's just a bulk term. E dot B is special. This so-called F wedge F, this is something that I can move to the boundary if I want. This is a total derivative of a Chern-Simons term at the boundary. But it's not the same Chern-Simons term we talked about before. That was an expression in terms of the Berry gauge field. This is just the ordinary electromagnetic field. So you might ask, if you don't know already, what does a Chern-Simons term mean if I add that for the electromagnetic field? What's the physics that's describing? And then the maybe most impressive thing that at least Wilczek pointed out, maybe other people knew it too, was this coefficient, which I can make dimensionless if I just put in an E squared by H, and I'll kind of explain at the very end why E squared by H could have been guessed from what we already know about polarization in the flux quantum. If I write it this way, then theta is dimensionless. And maybe the biggest surprise is that theta is indeed like an angle. At least, to be precise, the part of this effect that is determined by the bulk is like an angle. It's only defined modulo 2 pi. In that sense, it's very much like what we said about polarization. I said that once I tell you the surfaces, polarization is well defined and measurable. But if I only give you a unit cell and I don't tell you how that gets cut off at infinity, then only the fractional part, or only the part mod E in one dimension of polarization is well defined. Well, interpreting what the particle physicist said in our language, only the bulk contribution, only the fractional part of theta, theta mod 2 pi, is well defined from the bulk. So in understanding this term and how it relates to the definition in terms of an odd number of Dirac fermions, let me draw one picture about why you might guess just on physics grounds that an E dot B term in bulk has something to do with quantum Hall effect at the surfaces. And here's why, if you think about just the geometry of the way fields act. So I said this is an E dot B term. That means, for example, that if I apply an electric field, that should produce a magnetic moment. Well, suppose I put my surfaces into quantum Hall states. Then applying an electric field, well, if the top and bottom are in opposite quantum Hall states, then I will get currents that are perpendicular to the E field and kind of run around the topological insulator slab. So note that I've made an assumption here, which is that whatever material I had gapped surfaces. So the definition I gave before was that topological insulators always have gapless surfaces if I don't break time reversal. So I must have added a little bit of time reversal in order to gap the surfaces. When I do that, I put the surfaces in some quantum Hall state, and the interesting question is what quantum Hall state? Whatever it is, let's say it's got this sigma xy, there's a current running around and around, and that current gives me a magnetic moment which is proportional to the electric field. And if you work out the constant of proportionality, theta equal to 0 would be a system where my surfaces are in integer quantum Hall states. Theta equal to pi, now this is 1/2, would be a system where my surfaces are in half integer quantum Hall states. So half integer quantum Hall effect, where have we ever seen that before? Well, wait till the next slide. But just to understand what this is saying, this is another way to tell apart the ordinary insulator from the topological insulator. It's exactly equivalent to say theta equal to pi versus theta equal to 0 in the bulk as to say integer Hall effect versus half integer Hall effect at the surface. So we say ordinary insulator is a material that if I gap the surfaces has integer Hall effect. Topological insulator is a material that if I gap the surfaces has half integer Hall effect. And that is a definition where we can actually use experiments on graphene to connect it to the definition we gave before. So this is Philip Kim's data. I think he's coming later. And it's a difference between the quantum Hall effect in graphene and the quantum Hall effect in an ordinary material. So if I took an ordinary 2-dag, like gallium arsenide, the original quantum Hall experiments, then we see, well, Ne squared over h for sigma xy. And N is equal to, say, 0, ordinary insulator, 1, 2, ... In graphene, we see something different. And at least some of this, the fact that it's symmetric between plus and minus, you could guess from what Professor Levitov drew about the Landau levels. To be precise, the numbers that appear are minus 10. Well, it goes down to minus infinity, but let me draw something. Minus 10, minus 6, minus 2, 2, 6, 10, ... Well, what's special about these numbers? And to be precise, if I went up to very strong magnetic fields and low temperature, these plateaus, which are basically 4 Landau levels at once, changing as I go from one to the other, these would split because of interaction effects. But at least if interactions are weak, this is the pattern, and that's seen experimentally. This is one of the nice proofs that graphene has Dirac fermions, because if you figure there are 4 Dirac fermions in graphene, once I include the valley degeneracy and the spin degeneracy, then if I divide all this by 4 to figure out what 1 Dirac fermion should do, then I just get the half integers. Minus 5 halves, minus 3 halves, minus 1 half, etc. So it's a nice calculation if you want to try to convince yourself from taking the Landau levels in graphene that indeed 1 Dirac fermion is half integer Hall effect. But that's kind of how the picture hangs together, that if I could make the surfaces of a topological insulator gapped, which have an odd number of Dirac fermions, then they can't be in an ordinary integer Hall state. They have to be in a half integer Hall state. If I add together the 2 surfaces in parallel, like if I'm doing a transport experiment on the whole thing, I'll still see an integer. But if I look at this magnetoelectric effect, I will see what looks like theta equal to pi rather than theta equal to 0 if I can establish this connection between F wedge F and something at the surface like the Hall effect, which I want to do on the blackboard. So to kind of summarize, parts of this we've at least claimed before and parts I'm going to show. If I go into an insulator I mean the whole thing is gap, the bulk and the surface, then there can be a term of this type, and in fact the only term that can be present if I have time reversal is this one with either theta equal to 0 or theta equal to pi. The way that's measured, you can either take change in magnetic moment in an applied electric field or change in polarization in an applied magnetic field. And this term, the theta angle, at least for a TI, is computed by this integral of the non-abelian Chern-Simons form that we kind of motivated last time. But this sort of raises a question, which is, so far we've just talked about this as another way to compute the topological invariant. We had other ways to compute the Z2 invariant beforehand, so what use is one more way to compute something that only has two possible values? Why would you want to do this big integral, aside from mathematical cuteness, if it only takes two possible values? Well, the answer is you actually learn something about all magnetoelectric insulators. It turns out this term is at least part of the story, even if you're not talking about a topological insulator, but any magnetoelectric. And magnetoelectrics have been a big field for ages, so that kind of shows there's still something new that people didn't know. So in a way, this is a little disappointing because whenever we find one of these universal quantized values in this type of topological system, it seems like it's somehow related to E squared over H. If you want a quick picture of why maybe the people who were working out the modern theory of polarization could have guessed that there was something special about dP by dB for a three-dimensional material, let me give a quick argument and then sort of stress that this is actually valid in the interacting case as well. So the quick argument, which I can do more on the blackboard maybe if necessary, is the following. What we said about polarization in a 3D material so far is that it has a pretty non-universal or material-dependent quantum, or ambiguity. We said that the ambiguity of polarization, which is, if you like, if I make a gauge change of my wave functions, how much does the polarization change? It changes by an integer charge per transverse unit cell area. The idea of this was, if I terminate my crystal, then I've got, let's say my unit cell is a parallelogram. I've got one side of the unit cell that's my termination. I can stick on an integer number of charges per unit cell without breaking the periodicity, and that corresponds to a polarization or surface charge density of E by area. Well, that's not very nice because it depends on the area, but there's something else that depends on the area, which is, what is the minimum magnetic field I can apply and maintain Bloch's theorem? It's one flux quantum, H over E, per unit cell, which in terms of magnetic field is H over E times the transverse unit cell area. So in other words, there is a natural unit of dP by dB in a crystal, and the area actually drops out, so the units of dP by dB are E squared by H. Or in a sense, the quantum of dP by dB, because this, or the ambiguity, maybe is a better term, is E squared by H, and we know that whenever we have an ambiguity in something that's odd under a symmetry, we get two values which correspond to 0 and plus or minus a half. Those are the two values of the magnetoelectric effect. So a way to kind of summarize is E squared over H means something special in every dimension. In 1D, it's kind of the natural unit of conductance. In 2D, it's a unit of Hall conductance. And in 3D, it's the unit of the magnetoelectric effect. But the 2D and 3D things are very closely related because we said, in a sense, that saying there's a magnetoelectric effect, at least of the E dot B type, is equivalent to saying that there is a surface Hall conductance, which is something I want to show you. Okay, so to kind of wrap up with a couple more slides on the magnetoelectric effect, I claim that this was a useful spin-off of topological insulators, where you learn something about materials that you weren't even trying to study. So a general magnetoelectric effect, if I gave you Cr2O3, for example, as a classic magnetoelectric, then there are terms like this. There's a full 3x3 tensor response. Exactly which terms are non-zero depends on the symmetry of the crystal, but you might try to break it up into a scalar diagonal part and everything else, and that Chern-Simons part can at most contribute to the scalar diagonal part, because that is scalar. But even this term, it's not quite the whole story, and if you do quite a lot of work, this is one of the more technical papers I've ever been involved in, you get the following expression for the full magnetoelectric effect from orbital electron motion in a crystal. And I want to explain how this fits in briefly with other magnetoelectric effects you might know about. So this term, which in general has all 9 non-zero components, this is in a sense is the ordinary one, the one you would have expected just based on doing perturbation theory. When you think about calculating a response in perturbation theory, you've got electric dipole moment, magnetic dipole moment, energy denominator, and a bunch of other stuff that's kind of a correction that comes along to make everything work right. This is the interesting thing. This is the same Chern-Simons term of the band structure that I talked about last time. So this is always there in general, but it's not necessarily quantized unless I have a symmetry. Basically, if I have time reversal symmetry, then the ordinary part is 0, the topological part is quantized. If I took a material that breaks inversion, breaks time reversal, both these terms are there, and you actually have to sit down and compute them. So in a sense, the topological part is the whole story for topological insulators, but it's part of the story in all multiferroics. And even these two terms are, on some level, just 1/4 of the full story, which is that you can divide all magnetoelectric responses, just to tell you a little bit about magnetoelectric materials. So incidentally, if this theta term sounds very exotic, people had actually measured it in standard multiferroics breaking all the symmetries, like Cr2O3. If you convert their measurement to an angle, they measured theta of about pi over 24. So nothing's quantized in this material because this is not a topological insulator. This breaks symmetries. But it's not particularly small, not particularly large. But it does show that the value pi is not hugely different from what we already know about in other materials. Pi is fairly large, but not gigantic. The point of this table is when you think about an E dot B response, or any kind of EB response, the polarization could either come from essentially the electrons with fixed ions or motion of the ions, and the magnetization could either come from the orbital movement of electrons or from their spin. And what we've just computed, all that work was just to fill in this one box, but in many multiferroics, this is not necessarily the largest box. It just happens that, again, for topological insulators, everything is coming from this box, and all these others are 0. A minor comment is that while this box is not always the largest, it's actually the fastest and the one that doesn't degrade the material, so that's one reason why people kind of care about that box. So I think now is probably a good time to get back to the blackboard. Yeah, this is a typical multiferroic. Yeah, I think let me take a break from slides for now.
I have a question before you move on.
Yeah.
So if you choose that theta, that over there.
If I choose theta to be this.
Yes.
Yeah.
Why does that mean the integral isn't quantized anymore? Doesn't it just mean it is quantized in a number that's not 1?
No, I mean, it doesn't have to be fixed to any particular rational or anything. I see what you mean. No, the integral, its fractional part is it's not quantized to be either 0 or pi. The fractional part would be pi over 24, but I can still only shift it by a multiple of 2 pi. So it's just like polarization in 1D. It has an ambiguity of 2 pi n, but the number is well defined other than that. But the point would be, nothing keeps it from continuously varying. So that while in the topological insulator it has to be either 0 or pi, because any other value would break time reversal. So now let me... Is that... Okay. Any other questions before I get to the blackboard? Yes.
So can you measure this directly, in addition to also measuring the Hall effects?
One hopes so. So actually the closest thing to a measurement like that is in strained mercury telluride by Lorentz. With transport, not with a direct magnetoelectric measurement. The main problem is that in the earlier topological insulators like bismuth selenide and so on, it seems very hard to actually gap the surfaces. So, for example, if you think about how you would do it with a magnetic field, if you remember those pictures I showed from photoemission, the surface Fermi surface is a reasonable fraction, maybe 10 or 20% of the surface Brillouin zone. It's not zero unless I manage to fine-tune to the Dirac point. So without a lot of fine-tuning, if you just take an as-grown crystal, that corresponds to a very high surface density 2deg, which means that a reasonable magnetic field, you'll be at like 100 or 200 filled Landau levels where you don't usually see quantum Hall signatures very strongly. You want to get down to a few Landau levels, which we could do if we could move the surface right next to the Dirac point and then carefully apply a magnetic field. As far as I know, that hasn't yet been possible, but people are trying. But I would say to me, it is just as good to measure a clear transport signature of half integers in the Hall effect as it is to measure this by, for example, the technique that Obukov and Hill use is apply a magnetic field and measure the charge density that built up. The main issue in the mercury telluride is that the G factor is so large that your Landau levels in a magnetic field become quite complicated. You have to fit the Zeeman effect quite strongly. It's a big part of what you observe. What you really want to focus on is kind of the orbital Landau level effect. So, other questions before we go to the... Okay. So I need to explain a couple of things that flashed by there. Let's erase that. Okay, so the first, this electromagnetic Chern-Simons term is actually going to be part of the big story when we talk about field theories of topological phases, specifically the quantum Hall effect. So let's get a little bit of practice with it. So note one quick thing. This, in a way, is going to be easier than the thing I wrote down for band structures. The band structure thing was non-abelian gauge field coming from multiple bands in a band structure. This is abelian because the electromagnetic field is abelian. So I'm going to claim that this describes the two electromagnetic responses. You already know one, but maybe not the other. Of a quantum Hall system. So this is going to be a term I add to the ordinary Maxwellianum. The quantum Hall effect is a 2 plus 1 dimensional layer, so I'm going to have a delta of Z. And then I want epsilon ijk, where these are time x and y in some order. A sub I, partial j, a sub k. So I don't need that third term, AAA, because now my A's don't have any upper indices because I have an abelian field. So this is the whole abelian Chern-Simons term. So if I had this, what will this do when I look at currents and things like that that are measurable? So I said there are two effects, two responses. Well, when you have a term like this, you should figure out what does the current give. So this is a term in the Lagrangian density. If I take, to get the currents, let me just... Well, both the responses I'm going to talk about are of this form. It depends on whether I take A to be the time direction, which will give me a J0, which is a charge density, or a spatial direction, that will give me what we normally think of as a current rather than a charge density. So if I is equal to 1 or 2 spatial, or I is equal to 0, those are my two effects. So in the spatial case, well, let's think about it. This is like saying if I take a derivative with respect to one of these, then let's say if this is spatial, one of these has to be time. So for example, I could have the time derivative of the vector potential, or I could have the spatial derivative of the potential, A0. Either way, that's an electric field. So this gives me the result that spatial current, for example, Ji is epsilon ij Ej, where now I and j are just 1 or 2. So that's the Hall effect. That's saying if I write down this term and I compute the current from it, I get a spatial current that is transverse to the electric field. So that's good. That's the Hall effect. What about this? This tells us something interesting too, which you might not have thought about. This says that there's a charge density proportional to the applied normal magnetic field. So to be precise, there might have been one big constant magnetic field that was on to produce this quantum Hall effect. What I'm thinking about here, this is the linear response to small perturbations. This says, well, so 1 is what I'm calling spatial, 2 is time-like. Let me explain response 2, because you might not have thought about it. It says if I increase the magnetic field a little bit, then I increase the charge density where I increase the magnetic field. And if you want to think about that in a simple picture, if I had Landau levels, we know that the density of states in a Landau level is related to the magnetic field. So if I increase the magnetic field by a little bit in a region, it makes sense that there are slightly more states in the Landau level, so a little bit of charge must have flowed in. So that is indeed a physical response in any quantum Hall system. It's just kind of the electric-magnetic dual of the Hall effect. That adding a little... Oh.
Joe,
yeah.
What you mean is you keep the filling factor constant, and in order to do so, when you increase the number of states per Landau level, then you need to compensate that.
That's right. I mean, in the simplest case, I'm thinking about a spatial variation where I want to stay in the gap system, but I've slightly increased the magnetic field in one region, which means that if I'm still filling, let's say, exactly one Landau level, but the density of states, the spatial density of states per Landau level is now slightly higher here than there, so there's a little bit more charge density here than there. That's right. And it kind of has to be there almost by the way we wrote the term. So let's now try to understand dm by dE. Okay, so I already drew you a picture for dm by dE. Why, if I have a bulk E dot B term, so I said that F alpha beta F gamma delta is up to some coefficient. So this is my statement that E dot B, if I put in an epsilon beforehand, E dot B is the total derivative of what we just talked with over there, which is surface Chern-Simons. Or to be precise, when I think about what a total derivative means, whenever I change the theta angle, that is, theta is the coefficient of a bulk E dot B term, then if I do that, and to be precise, if I do that and I don't close the gap, which would be the case if I've got a gap surface, When I change the theta angle, then there is a quantum Hall layer, or Hall layer, of size delta theta times e squared over h. And if I want theta to have units of 2 pi, then there's a 2 pi there. So for example, if I go from 0 to pi in theta, I get an e squared over 2h layer, or 0 to minus pi would give me minus e squared over 2h. What does that ambiguity mean? Well, I gave you a definition of the polarization ambiguity, which is that I can keep the same bulk unit cell and change the surface charge density, but only by an integer amount. The way we think of the magnetoelectric ambiguity, which is e squared by h, is that I could keep the bulk the same, but add integer quantum Hall layers.
So,
Let me...
what do you mean by size? Because this delta theta e squared over h is homogeneous to momentum.
I didn't hear the last part of what you said.
So what do you mean by size? Because the...
Oh, I mean the magnitude of the Hall effect. I don't mean spatial size. I mean, this is the sigma xy. Okay, sorry. Yeah, the spatial extent depends on, over what distance do I change delta theta. So what does it mean to say that bulk theta, or let's say theta mod 2 pi, is determined by the bulk? In other words, I can add 2 pi times an integer. Well, the simplest might be to think about actually doing an experiment where I've got my TI slab, say. Focusing on the top surface, we know we've got some, let's say, Dirac cone here. I can change the filling of that Dirac cone without changing the phase. So essentially the surface is a two-dimensional electron gas like any other two-dimensional electron gas you thought about, except that it's got an odd number of Dirac cones. So changing the filling of surface state, for example, by surface doping, well, that will affect, when I now come along and put on a magnetic field, that will affect what surface Hall state I'm in. How many surface Landau levels are filled. In other words, I could imagine that by changing the surface doping, I would effectively be adding some number of integer quantum Hall effects on the surface. So I'm changing the surface sigma xy every time I pass through a Landau level by e squared over h. In other words, with polarization, the ambiguity was the freedom to add integer units of charge. Now the freedom you could think of as the freedom to add integer quantum Hall layers. I could take my same material and staple on some integer quantum Hall layers without modifying the bulk, and when I measured the whole thing, I would get a theta angle that had shifted by an integer times e squared over h. But if I don't have fractional charges, then I can't get some non-integer shift. So in particular, the half integer remains observable, but which half integer I see in an experiment depends on the details of the surface. But I should always see a half integer. Yeah.
Sorry, can you repeat that argument? First of all, why does changing the theta angle lead to a quantum Hall layer?
Well, it was a total derivative here. So I had, let's say, theta times that. That's not theta. That's theta. So I had theta times that. And then I said, well, okay, this thing is a total derivative of something. So that's theta times the derivative of that. So then partial derivatives, I can switch this over to d theta times, well, this thing is the Chern-Simons. So in other words, where there's a change in theta, there is a Chern-Simons term. So if I think about this happening rapidly in some region, let's say theta is a step from 0 to pi, then this would give me a delta function right where that step occurs. So I would have a delta function layer, which is exactly what I wrote down for the quantum Hall case.
Okay. But why does a change always have to be integer?
Oh, okay. Well, change here, I mean something slightly different than change there. So my picture for this is I've got, say, a material with theta not equal to 0. But again, it's only defined modulo 2 pi. So it could be pi if I were talking about a topological insulator. Let's just say something. And out here I've got vacuum. Let's define our vacuum to have theta equal to 0. Then the statement on the left side of the board here is that at these surfaces, I could rewrite the electromagnetic effect of integrating theta f wedge f over the bulk as, in this case, the total change in theta is, let's call this, this theta is not equal to 0, so this is a theta e squared over 2 pi h. Up here I'll have a minus theta. These are my quantum Hall layers at the top and the bottom. So here I'm talking about the spatial change of theta gives me a localized quantum Hall layer. When I say change over here, what I mean is I could come along with this material. I want to explain now what does it mean to say that theta, if I just give you the material unit cell and I don't tell you about the surface, then theta is only well-defined modulo 2 pi. You could come along and say, well, I don't want to terminate the surface the way you did. I'm going to put some extra electrons here, which means I'm going to fill a higher Landau level. So for example, if this was business selenide, I might have one where my surface chemical potential is right near the Dirac point. So I get, say, sigma xy of e squared over h or minus e squared over h. You might have a heavily doped surface, which means that when you put on the magnetic field and put your surface 2-deg into a quantum Hall state, you're at 50.5 e squared over h or something like that. So that's saying that the definition of change over here is that different details of the surface preparation in practice with the same bulk unit cell, the change in theta that gives me the quantum Hall layer will change, but it only changes by an integer times e squared over h. So the fractional part of theta is uniquely determined by what the material is. The additional integer quantum Hall layer that I measure when I do an actual experiment, which you could think of as the surface Landau level filling, that depends on microscopics, but only in an integer way. Good, thanks for the question. Yeah?
Just why in the classification Ludwig and others didn't take in account these terms? They only take the written term and the topological term.
I guess they didn't precisely need it. So another way to state the question would be, only for some of the items in the table do we know a physical response like this. And the reason why a physical response like this is kind of important is that the existence of theta, a well-defined physical response that is just quantized by symmetry, is a proof that the state is actually well-defined even in the presence of interactions. For some of those elements in the table, we know that if I'm allowed to turn on interactions, I can connect two different phases of the non-interacting problem. So it's actually, to some extent, an open problem to figure out, at least in dimensions above 1, exactly which of the topological classes in that table are stable once I turn on interactions. But here, this theta is a bit different from, what they're doing is more like the Chern-Simons integral of the non-abelian Berry phase. That is, the math they're doing is math of the electrons. This is kind of math of the E and M field. So this is all abelian. But if you like, where this gets quite subtle, in some of those classes, there's a conserved charge. We'd say a conserved U1. And then you can often do something like this. The toughest classes to deal with are things like a superconductor. So a superconductor doesn't have a conserved charge current. It only has a conserved energy current. Conserved energy current, at best, if you want to define a physical response, you have to do it with gravity or something like that. You can't do it with electromagnetic field, and that turns out to be quite subtle. So I wasn't planning to say anything about it, but the Stony Brook crowd, which is represented here, could probably tell you a bit more. Okay. Good. So the surface state so far, it seems like there is a difference in the quantization of the Hall effect. It's half integer instead of integer. So that's kind of consistent with the picture, which even works in the 2D topological insulator, that the way we stabilized an ordinary metal against localization was that we sort of cut it into two pieces. We took half of a 2-deg and put it on top. Half of a 2-deg, well, that means, say, 1 Dirac fermion. These are just kind of words, but the more precise sense would be sigma xy half integer at the top and 1 at the bottom. If I measure both of the surfaces together, I get back to a normal 2-deg. In the same way that if you look at Lorenz Monkamp's charge conductance measurement, when he combines the two edges together, he gets 2e squared over h conductance, which is exactly the conductance of one quantum wire. So it's like one quantum wire was split up, put at the top surface and the bottom surface, and then measured. And what protected that wire from localization was the fact that it had been chopped in two and kind of separated from each other. So the same thing is sort of true here, but there are important differences between the 2D surface and the 1D edge. Let me say a little bit about those to kind of motivate this question. How is the TI surface different from graphene? So it's different in a factor of 2, odd number of Dirac fermions versus even number of Dirac fermions. But what I want to convince you is that even in the non-superconducting case, there are kind of interesting consequences of that. And in the superconducting case, there are arguably even more interesting consequences related to this idea of Majorana fermions that I will sketch. Maybe it will motivate you to read more. I think Majorana fermions would be a course in themselves. There are now so many papers on them. Okay, so if I looked at this surface, this is now some two-dimensional system of electrons. How is scattering going to work? So let's draw the surface Fermi surface. In other words, I'm thinking about my two-dimensional metallic electrons before I've put on whatever little magnetic field or whatever is necessary to gap them. Then, okay, if we repeated our argument, let me draw some spin directions. This is the kind of thing people can measure in photoemission. So the argument we gave before about not being able to scatter between the members of the Kramers pair if I have time reversal invariance, that forbids this, or similarly that. So there's no 180 degree scattering. And an experiment claiming to see this, I unfortunately forget the first author, but it was Yazdani's group at Princeton. There's a technique that came from work of Seamus Davis and Dong-Hai Lee on high-temperature superconductors, actually, which is to analyze, basically by taking a Fourier transform, what you see in a STM measurement of a surface in terms of what scattering processes are happening of the quasi-particles there, this quasi-particle interference spectroscopy. If you apply that to the surface of a TI, you indeed see that there's no scattering of this type, but it's different from the 1D case in that there still is some scattering. Nothing prevents me from doing that. The amplitude to do this kind of goes to 0 as I get close to the 180 degree part, but at 90 degrees, for example, there's plenty of scattering. So at least at first glance, if you measure the conductance here with finite disorder and finite size, you'll see some non-zero but not infinite conductance of the surface state. So it's interesting to try to figure out what is a case where you will see dramatically that there is some difference as a result of the 3D topological insulator. And I'll tell you maybe the most direct one I know, and it might be, you could motivate it either by trying to find some interesting transport signature of a TI or by thinking about defects. So the other motivation for what I'm going to tell you would be topological defects in a topological state. Let me give you maybe 2 examples related to TIs. So I haven't said anything about weak topological insulators. Maybe now's a good time. Actually, let me do the 3D. Let me do the strong TI first, and then the weak TI. So the 3D strong TI, I want to think about a magnetic field line. Through a hole in the 3D TI is maybe the easiest way to start. So this will be, if you're wondering how you could realize this, well, in a minute we're going to talk about, suppose I have a superconductor with vortex lines through it, and that sits on top of the 3D TI, then I might expect that the magnetic field lines from the vortex continue through the TI. So I could think about something like this. I drill a hole, and through that hole I've got some magnetic field. So, okay, if the hole were big enough, I would think that I could put my surface Dirac fermion on the outside of the hole, and the effect of the magnetic flux lines will be to generate an Aronoff-Bohm flux for that surface Dirac fermion. So we need to figure out what does that Aronoff-Bohm flux do. So let's think about a fairly long hole. Or it turns out that for everything I'm going to say, I could think about either a hole in the TI, or I could think about a nanowire of TI with the flux going through the nanowire. It doesn't really matter, because from the point of view of the surface state, these are about the same thing. Okay, so I've got my Dirac fermion. It now sees a flux, which means I have to quantize the surface Dirac fermion with a flux through it. And let me first think about what I would expect to happen in a metal cylinder or maybe graphene. Because I said I would like to focus on cases where you get a difference between the TI and an even number of Dirac fermions. If I take an ordinary metal, then I expect the following thing for conductance. Along the wire. And let's make a plot of the flux through the wire. So if you've ever studied your mesoscopic physics, you know that there are actually 2 kinds of flux dependences you can see in this experiment. You can see H over E periods, which we think of as the Aronoff-Bohm effect. Or you can also see H over 2E periods, which are related to disorder averaging and were originally observed, I think, by Charvin and Charvin. So both of those are there, but the 0th order signature, if you don't want to worry about the details too much, is that when you put in a little bit of flux, the conductance goes down because you are starting to stick a phase in there that the electrons don't really want. And exactly which period you see turns out to depend on the disorder strength. In general, if you have a very clean system, you would expect to see H over E. As you turn up disorder and get a more diffusive metal, you would start to see a period H over 2E dominate. So the smoking gun that experiments in Dresden, I think, are trying to see, and experiments at Purdue also, is that if you have a topological insulator instead, then something a little bit weird happens, which is that, at least if it's long enough and a little bit dirty, there's the opposite feature, that the conductance goes up. And actually, if I make it long enough, then the conductance becomes basically a delta function at pi flux or 3 pi flux or whatever. And this height will become E squared over H. And let me try to give an illustration in words of what's going on. So claim in a TI, well, the simplest way to state the claim is that pi flux in a TI is like 0 flux in graphene in a nanotube or a normal wire. So the more precise statement is that if I do this experiment and put pi flux through, I'm actually guaranteed, I might get other modes as well, but at a minimum, I get one so-called helical edge, basically one edge of the 2D topological insulator with one mode going up and one mode going down. So I will show you some data to try to convince you that this is true, but if you want a rough hand-waving picture of why this might be true, think about the following. In the topological insulator, we said that the spin is uniquely determined by the momentum. As I move an electron momentum around this cylinder, then the spin rotates through 2 pi, which gives me a -1 Berry phase. That -1 Berry phase, turns out, if you do it carefully, there is a -1 Berry phase. And that -1 Berry phase combines with the Aronoff-Bohm phase of pi flux, which is also -1, to get me back to no phase, which would be like 0 flux in a material that didn't have this strong spin-orbit coupling. So if you like, the pi flux is there to compensate the material's own Berry phase, which is another source. I don't know that you would particularly believe this argument without data, so I will not try to justify it further, but I can show you data. And there is even a tiny bit of experimental data, as I said. So in a weak topological insulator, a similar effect is even easier to see. And this is due to my colleague Ashwin Vishwanath, who's coming later. Well, I said a weak topological insulator in 3D is like maybe the easiest way to think about it is layered 2D TIs, or 2D TI is just another term for quantum spin Hall effect. So suppose I had a bunch of layers, and then at some point, well, let me first draw no defect. So I've got these planes, and each one of these planes has a helical edge. And incidentally, if you're wondering why they're called weak topological insulators, you can see that once I turned on disorder, if I had an even number of these planes and thought about scatterings between the edges, the even number, it looks like, could go away, and the odd number couldn't. But actually, we believe in practice that the surface of the weak TI is somewhat stable to disorder. I can imagine a defect where one of these planes ends inside the material. So I've got some dislocation, edge dislocation, where now, think about if I took a side view of the material, I've got a bunch of planes, but then at some point, I do this kind of thing. Then this is all saying that that kind of crystalline defect, so here, we left the material the same and we just added a magnetic field. It turns out that's what I have to do in the 3D topological insulator, the strong one. In the weak one, it should be that some crystalline defects, like for example this edge dislocation, or there's kind of a topological analysis of dislocations. It turns out even screws and other kinds will have the same physics. There should be a helical edge bound to the dislocation. So those are two quick examples of how, when you think about topological defects, in this case, it's at least a topological defect in the sense that there's an Aronoff-Bohm phase. This is kind of warm-up for is topological defect in the superconductor, where I'll show you a couple slides. Those can have interesting physics, which you can use to probe the fact that they're topological. So let me now say a little bit about the superconducting case, which is going to be, I think I'll come back to at least mention some work on that. But let's think about two kinds of topological superconductor. So I flashed up this 10-fold way table. And this included some topological superconductors. What that meant was that the Bogoliubov-de Gennes Hamiltonian of quasi-particles is topological, in the sense that we've talked about with topological invariance and maybe surface states and so on. And actually, there's one experimental system, at least, that we believe is topological in this sense. Helium-3 is a neutral superconductor, or a paired superfluid, if you prefer. It has one phase that is totally gapped for the quasi-particles. That's the so-called B phase. The problem is that you usually see this phase at a couple of millikelvin or lower, and it's very hard to do direct experiments to see the surface state. But the general belief is that the B phase of superfluid helium-3 probably does have some kind of surface state with gapless quasi-particles. And again, this is atoms rather than electrons that are doing the phase. But since that's hard to measure, a different approach would be to try to make something using ordinary non-topological superconductors and single particle topological insulators. And I think I will save the pictures for the slides, but let me just quickly say what's special about the Bogoliubov-de Gennes equation, and why are there so many papers on the archive about topological superconductors and superconductor semiconductor junctions and all that? Why do people care so much? Okay, so let's think about what I said about the Bogoliubov-de Gennes equation before, which was that it has sort of an automatic particle Hall symmetry, or E goes to minus E. Another way to state that is that the physical spectrum that has half as many states as the BDG spectrum. what I mean by that is, suppose I took a system that had a ground state. So I'm looking at excitations relative to the ground state, which is at 0 energy. I can't go below the ground state in energy. I might have a gap if I'm in an S-wave superconductor or something. So let's say, maybe as a function of k, this would be my energy spectrum for excitations. If I were to convert that, and this could even be, this doesn't have to be a superconductor or anything. You can take an ordinary single particle problem and write it in Bogusubov-de Gennes. And what you will get is something like that, where one physical level at a positive excitation energy E became two levels, sort of particle and whole levels, one at plus C and one at minus C. And just in case, if you've never heard of it before, I don't want to explain all the details of what a Bogusubov-de Gennes equation is, but where it comes from is, we know that in the mean field theory of a superconductor, we have terms like delta, C dagger, let's say if it's S wave, something like that. So this now doesn't conserve particle number, but it's still quadratic in terms of the Fermi operators, which means we can solve it by Bogusubov rotation. In that process, you're led to Hamiltonians like this. Okay, so that's saying that every physical electron level is a pair of levels in BDG, and that's fine. So if we were thinking about a discrete system, I would have, say, level, level, and then level, level. Maybe I've got 3. So everything's symmetric, and that's nice and fine. But there's something very special that can happen. So in other words, this pair are one. It might be a Bogusubov fermion. It might be some superposition of a physical electron and hole. That's fine. But it's still one fermion. To be precise, it's a complex fermion. It's something that is distinct from its antiparticle in a way I'll talk about in a second. But what's special is, suppose I have a level here. Well, actually, maybe some physical system, I write it down, I solve the Bogusubov-de Gennes equation, and I find that there's a level at 0 energy. Well, only at 0 energy is E equal to minus E. So it's possible that we have an isolated E equal to 0 level that is its own pair. To be a little bit more accurate, what you find in systems with unbound Majorana fermions, say, is that there are two levels at E equal to 0. Maybe, to start with, if the system is finite, they're split a tiny bit away. The reason I drew them differently on the horizontal axis is that maybe they're at different edges or different ends of the system or something. As I make the system bigger and bigger, they become two essentially independent levels at 0 energy. And if I've got a level at 0 energy, it's very stable. If it can't mix with a pair, one level at 0 energy can't move away by itself. It needs another level at 0 energy to talk to. If that other level at 0 energy is in a different part of the system, then they can't really talk to each other. So one of these 0 energy levels is very stable. And now the last step is, what does one 0 energy level in Bogusubov-de Gennes correspond to? If over here, two levels in Bogusubov-de Gennes was one ordinary fermion, well, the answer is one of these Majorana fermions. So what Majorana fermion means in our language... yes.
Is it possible to do all this without doing a mean field operation?
Oh, that's a good question. I think... in one dimension, yes. In higher dimensions, I'm not absolutely sure of a good example. I think, in general, this comes up with the tenfold way about, is it stable to think about things that you compute using the Bogusubov-de Gennes argument beyond mean field theory? I would say the general belief is yes. That is not to say that they're always stable interactions, but there are at least cases where this makes sense, but I've never seen a really clear proof of it. In 1D, the situation is better. It turns out in 1D, and this is work by Fidkowski, Kitaev, also Shi Chen. There are several groups that did this, but in 1D, there is actually a generalization of that non-interacting classification to the interacting case. There are a couple of ways of doing that. One is with matrix product states, actually. So in 1D, we know very well even the interacting states, and everything makes sense, and they can have Majorana fermions. In higher dimensions, someone in the audience who knows more can correct me, but as far as I know, there is no real proof that the Bogoliubov-de Gennes picture still applies beyond mean field theory, but we mostly believe it.
So you said that when you do this, when you go to non-blue space, you double the number of levels. But you also said that this zero level state, zero energy state, can be localized, or the two states can be localized in different parts of the system. So how does that?
Well, the answer must be that one of these is somehow half of an ordinary fermion. And that's what I want to try to sketch. So yes, there must be something very special about one of these. And the answer is that you might think that a two-level system is the smallest thing in quantum mechanics. A spinless fermion is a two-level system. So I haven't yet told you, but remind me to, before we run out of time, what is an example of a physics system that would actually do this? But let's say that it did this. What would it mean? So a complex fermion, which people sometimes call a Dirac fermion, but it doesn't mean, here Dirac doesn't mean relativistic, it means complex. This would be something like the electron. So C is not the same thing as C dagger. We could think of this as creating an electron. If you wanted, you could think of this as annihilating an electron or creating a positron. So, for example, these are really different. They have different charges, etc. And the physical example of a particle that might be a Majorana fermion is actually the neutrino. So we don't really know if the neutrino and the antineutrino are different particles or the same particles. Majorana's proposal was originally about this kind of thing. What if the neutrino and the antineutrino are actually the same thing? How could that work? To be more precise, he found a set of solutions of the Dirac equation for a fermion that we could think of as, you can choose your favorite normalization. Let me put it just like this. You could think of them as real and imaginary parts of a Dirac fermion. So these are still Fermi operators, but they don't have well-defined charge. Yeah.
When C is not equal to C dagger, isn't that a violation of charge conjugation?
No. I mean, all the time we deal with C and C dagger operations. Okay, I don't mean to say that this is an invariance of the Hamiltonian. This is not a symmetry, but I can create an electron, and that electron is a different particle from the system where I created a positron. Or in other words, I can create the operation of creating an electron and annihilating an electron. Those are not the same thing. That's all I'm saying. But creating a Majorana and annihilating a Majorana are actually the same thing. That's what's kind of bizarre. So, for example, this is my Majorana operator. If I try to take the Hermitian conjugate of gamma 1, I get back gamma 1. Same thing for gamma 2. Like, that's why, in a sense, you could think of these as real fermions rather than complex fermions. So, what I've just done, although it requires a lot of thinking about how would you expect particles like this to behave, you can take one complex Dirac fermion, which is a two-level system, and write it as two independent Majorana fermions. And actually, this has a long history, well before the modern fuss. So, for example, when you solve the transverse field or quantum Ising model, the 1 plus 1 dimensional quantum model that's basically the two-dimensional Ising model in disguise, when you solve that, you don't really solve it in terms of complex fermions. You wind up solving it in terms of Majorana fermions. A consequence of that is that its central charge is 1/2 which is the central charge of a free Majorana, while a free complex fermion would have central charge 1. So Majoranas have a long history, but what's fairly new, I guess, is finding systems that create isolated Majoranas. So in other words, you could almost think of it this way. You could always rewrite, if you wanted to, you could take whatever Hamiltonian you have in terms of C and C dagger and rewrite it in terms of Majorana fermions. And then you haven't really found isolated Majorana fermions. You've just rewritten your Hamiltonian. It's not that impressive. But there are cases, and the simplest one is a so-called P plus IP superconductor, where you would create these isolated Majorana excitations. To be precise, the two-dimensional P plus IP superconductor has Majorana edge modes running around, and the one-dimensional P plus IP superconductor is basically this model studied by Kitaev that has isolated Majoranas at the ends. So to give you a reference, I think if you like Majoranas, you should definitely look at this paper. Reed and Green, sometime around 2000, explained why a P plus IP superconductor has, first of all, a Majorana edge, and this is what 2D state. And second, it has Majoranas in vortex cores. In other words, if I take a 2D P plus IP superconductor and look at the Bogoliubov-Dijen equation near a vortex, let's say that up here is my superconducting gap. So P plus IP, I'll say a little bit more in a second, but it is a fully gapped superconducting state, like S-wave, but more interesting. Inside a vortex, there are both ordinary trapped states. So these come in pairs and are ordinary trapped, they're called Caroli-Matricon-Dijen states, to be precise, but they're basically just ordinary defect states, bound electron levels that happen to exist in the vortex. But there should also be one Majorana state in the vicinity of the vortex, and that Majorana we would love to find for a number of deep reasons. So the deepest is probably that it has not just fractional statistics, but non-abelian statistics. I'm going to tell you in the next lecture how to implement abelian fractional statistics with Chern-Simons theory. I doubt we'll get to the non-abelian case, but I can at least tell you what it is, even if I can't show you what it is, but I can show you the abelian case in the finite amount of time we have. So the reason why Reed and Green cared is that actually there's a quantum Hall state, the Pfaffian state, that people knew about beforehand that has these same properties. In fact, the Pfaffian state is kind of a P plus IP superconductor of composite fermions. So what is this? What is this P plus IP superconductor? Well, if you want a very hand-waving picture for why it might be different from ordinary S-wave and have Majoranas, S-wave, we have delta, well, this thing I wrote here before, this is S-wave. So S-wave is a spin singlet superconductor, meaning as I go around K, as I take K around the Fermi surface, I use all the spin states. What if I took I could take a spin polarized superconductor. In other words, then the spin state is a triplet. Which is symmetric. So the orbital state must be antisymmetric. And the simplest case would be a P wave. So if I take a superconductor using, say, only a half metal. So half metal means a state where all the electrons at the Fermi level have the same spin. If I could make a half metal superconduct, which is a highly non-trivial thing, then that should be a P plus IP superconductor. In other words, if I do this, making a now momentum dependent in a P wave way delta, and only using spin up, which would be a superconducting half metal, well, that uses only half as many electron states as the S wave. In other words, we've only used upspin, not down. So we've used half as many states as usual. Which is a clue that it might be different from the S-wave superconductor. So the one problem with P plus IP superconductors is that we don't have hugely convincing evidence of one yet. Maybe the material that people have been hoping for, but the experimental situation is pretty uncertain, is strontium ruthenate. So this is definitely an unconventional superconductor, and there's been a lot of beautiful work by people like Maeno and Mackenzie and others trying to figure it out. I would say not totally clear that it is indeed fully gapped P plus IP of the topological type, but we know a lot about it. So maybe we should try to make one a different way. So we do have this Pfaffian state. There is a quantum Hall plateau that we think should have Majorana fermions, but despite a lot of investment in experiments to try to see that, it hasn't quite worked 100% yet. So let's try to build a topological superconductor, even if nature doesn't give us one. Yes?
Is strontium ruthenate a half metal in its normal state?
No, it isn't.
Is that one way to try to get this superconducting? Something that's half metallic and it's...
That's right. The problem is they don't seem to go superconducting. In general, the way we make half metals is to take things that are very magnetic, and things that are very magnetic often don't superconduct because you could see that the magnetic field would tend to destroy the superconductivity. So you could try to proximatize a half metal. Actually, that's a good question because it lets me illustrate what's very clever about the proposal I'm going to show of Fu and Kane. The problem, you might say, well, okay, maybe you give me a half metal and I try to proximatize it. Proximatize means you put it next to an S-wave superconductor. The problem with proximatizing a half metal well, that basically means adding S-wave pairing terms to my system. But this S-wave pairing term doesn't actually connect any states. It can't do anything to the half metal because this always has one downspin in it, and there's no downspin for it to act on. So it'd be great if we could make something that was kind of like a half metal, but actually had a proximity effect to a normal S-wave superconductor. And once that proximity effect kicked in, it would become topological. What a great material that would be. So what material could do that? Well, look, there are celebrated experiments claiming that it does happen.
Well,
but it might be unreasonable.
If you wanted to induce, for example, an antiferromagnet by using the proximity effect of a superconductor, you have two completely different...
That's right. No, for the half metal it doesn't work. But let me show you a material where it's much more natural that the proximity effect... It creates a slightly different P wave, but not this P wave. And this other kind of P wave is also topological in the same way. So maybe ask me the same question in 5 minutes if you're unconvinced. So these are the pictures for what I showed you before. This is an actual experiment, although this one is not in the regime that shows the interesting effect, but this is the nanoribbon pierced by a flux. Incidentally, if you want to combine the two things I talked about of superconductivity with Majorana fermions and nanowires pierced by flux, there's a nice paper by Cook and Franz, which is on how you can use that to make Majoranas, and Cook is here, so you can just ask her if you don't feel like reading the paper. This is the numerical calculation. Let me skip that because clearly there's interest in Majoranas. This is the doubled Bogoliubov-Duhem spectrum. Okay, so this is the magic material. Turns out that the magic material is the surface of a 3D topological insulator. That's why I'm talking about it. So think about what we've already said about the 3D topological insulator. It has a single sheet of the Fermi surface, and that means it's kind of like the half metal, because the half metal has only one spin direction at each momentum. So does the surface of the 3D topological insulator. At least in the simplest case, if I took bismuth selenide, that's only got one spin direction at each momentum. But which spin direction it has changes as I change the momentum. It rotates by 180 degrees as I go from here to there. So it's not spin polarized. That means it might not be as good for spintronics or something, but it's very good for proximity coupling. In other words, this is a one-sheet metal rather than... sheet means how many Fermi surfaces there are once I include spin. Normal metals have two sheets at least because they're spin up and spin down. The surface of the 3D topological insulator is a one-sheet metal, like the half metal, but it's a one-sheet metal that does strongly couple to the proximity effect. And then what Fu and Kane showed was basically not just that, but if you take this superconducting state, which is the proximatized 3D topological insulator surface, then that is topological. It's a little bit different from what I talked about. So the P plus IP superconductor of the half metal, a clue that that breaks time reversal is the I. So that's a time reversal breaking superconductor that we should probably find in a weakly magnetic system or something like that. In fact, that's sort of how one way that people like Cam Moeller have looked for the P plus IP in strontium ruthenate. This is a time reversal symmetric but still topological 2D superconducting layer. So as the picture of what experimental consequence this would have, this is kind of the... I don't know if you have Radio Shack in France, but it's a place where you buy a bunch of cheap electronic things and put them together. This is the Radio Shack way to make a topological state. You take your ordinary S-wave superconductor like aluminum, you take your 3D topological insulator like bismuth selenide, and what Fu and Kane pointed out was that in principle, if you just stick these two together and make a vortex core of the superconductor, well, the proximity effect of the superconductor gaps that helical mode I was talking about. So anyway, you've got Majorana states at the edges, at the boundary between the superconductor and the TI in the vortex core. Similarly, I could have a Majorana state running around the boundary. This isn't actually the way that people have mostly been looking for Majoranas, because 3D topological insulators, with the exception of strained mercury telluride, are not particularly bulk insulators. But it motivated work by groups at Caltech and Maryland and maybe elsewhere, saying that if you took an ordinary semiconductor in a magnetic field, you would get something that is in principle less stable but is easier to work with in the laboratory. So it's a different kind of superconductor-semiconductor junction, but that's what groups like Cohenhoven, or Morik et al., the Cohenhoven group at Delft, have been using to try to publish high-profile papers on finding Majoranas and that kind of thing. So, it's a very rapidly developing field. I don't think the last word is said yet, but it seems like at the moment, even though we haven't found Majoranas in the quantum Hall case maybe, or we haven't found just one material that's a P plus IP superconductor, junctions kind of this type do seem to be a way to find Majoranas. So I think that's probably all I'm going to say about Majoranas. It is a large field, and there are other things I want to cover. But if you have questions, I guess I could try to answer them outside the lectures. What I will try to say is, so far what I've said is already kind of an interesting property, that a Majorana is a subdivision of a two-level system. You might think that a two-level system can't be subdivided, but it can. That's kind of a hint that a Majorana might be a very good quantum memory. If you could take one qubit, which is one two-level system, and store it in two spatially separated parts, that should be a very stable way of storing the qubit. A much deeper fact about Majoranas is that, at least in 2 dimensions and above, they tend to come along with a very strange kind of braiding statistics. Sort of if I move Majoranas around each other, weird things happen. And that, I can at least give you a sense of what that means. That, to me, is even more exciting about Majoranas, and the experiments so far have just been concerned with trying to prove that there are these zero energy states. The next step, I think the real holy grail sort of, would be to show that these are associated with non-abelian statistics effects. That would be, aside from possibly being a good quantum computer, just on a fundamental level, that would be an amazing breakthrough. So I see it's lunchtime. Oh, sorry, not lunchtime. Coffee time. Sorry, I've been in the 11 o'clock slot so many times. I've gotten used to finishing at lunch. But either way, if there are questions, please fire away. Otherwise, I owe you a break.
So, it's the ultimate proof to say that we have Majoranas. Will it be through their statistics, or?
Well, I guess you could sort of prove. I would say a zero bias peak with the right checks on it would probably prove that there's something like a Majorana there. It wouldn't necessarily prove that there are these interesting properties of it. So an example in the fractional quantum Hall effect, there are some experiments in the fractional quantum Hall effect that we think of, and I will tell you about this, that we think of as showing that there's fractional charged particles. Then there are different experiments that, for the most part, haven't been possible yet to show that there are fractional statistics of those particles. So I guess I would say we've proven that there are Laughlin particles with fractional charge. We may not have completely proven that they have fractional statistics. In the same way, if we can show that there are Majoranas, it would still be another step beyond that to show that they have non-abelian statistics. And one reason why I care about the non-abelian statistics is that that's kind of unique to condensed matter. So suppose the Majorana turns out to be a Majorana, suppose the neutrino turns out to be a Majorana fermion. Then particle physics would have Majoranas, we would have Majoranas. But in a neutrino particle like that just has ordinary fermionic statistics. There's nothing non-abelian about it. So it's really our Majoranas are better than their Majoranas. But to prove that they're better, we need not just the zero bias thing, but actually the non-abelian statistics thing. So I will not prove to you that Majoranas have non-abelian statistics, but I will at least tell you enough to know what non-abelian statistics are. Any other? Yes?
So what's the characteristic of this proximity effect item? Is that basically asking for a normal experimental setting? What's the estimate of how far the Kubrick can tunnel into this?
Right, that depends on the coherence length of the superconductor. Okay, it depends a little bit on what it's proximatizing, but a typical scale might be 100 nanometers or so for proximity effect into, I mean, it's very material dependent. But depending on the superconductor you use, so in a superconductor, okay, let me think about this. At least, okay, I don't want to make a general statement because I don't know the general answer. At least for aluminum proximity effect into 3D topological insulators, I think the scale of proximity lengths that people are measuring is somewhere of order 50 or 100 nanometers. I don't know that there's any intrinsic limit on that. But people can make films, for example, that are bulk-like in the sense of the top surface and the bottom surface are basically independent, but are still much thinner than that 50 or 100 nanometers. For example, the MBE group in Beijing does that with bismuth selenide. So it is possible to make a thin enough film, and you could also do it with strained mercury telluride, as I said. So at least in principle, the proximity effect is probably not the main weakness. I think the main weakness with this proposal is that you've created Majoranas that are kind of buried in the middle somewhere, so it's not very easy to tunnel into them or otherwise see them. That's why it's a little bit easier to have systems where the Majoranas are kind of at the end. If you want a proposal like this where the Majoranas at the end, then that was the point of this proposal I mentioned, where you take a topological insulator nanowire, lie it on top of the superconductor, and kind of look for the Majoranas which now sit at the ends of the TI nanowire. So that might be more experimentally accessible. Other questions? Yes.
Yeah, you say that fermions have to be far apart of each other. Can you just say a little bit more?
Yeah, at least they're kind of topologically protected if they're far apart from each other. If they're close to each other, then in general, it's a bit like degenerate states in quantum perturbation theory. If I have two levels that are close to each other and there's no symmetry that protects them from mixing, even a small perturbation will open up a large splitting because the energy denominator in second-order perturbation theory is 0. So this is kind of why there's, in general, level repulsion. You don't usually see degeneracies or near degeneracies between levels that can mix with each other. So if they're close to each other and there's no special symmetry, then they could kind of mix, and you'd expect this to kind of become two levels in the Bogoliubov-Degen spectrum that are split away from 0, and now you're back to an ordinary fermion. So somehow you have to keep the two Majoranas from mixing. Normally the easiest way to do that is spatially. If the Majoranas had some symmetry associated with them, then you wouldn't need the spatial separation.
And what's the scale of these?
So the spatial size of the Majorana, for example, in the P plus IP superconductor, the spatial scale of the Majorana decay is set by the coherence length of the superconductor, I believe. So that that varies widely between something like a cuprate, where it's tiny, a few nanometers, to something like aluminum, where, as I said, it's more like tens of nanometers. So I could be wrong, but my general guess would be that the length scale for Majoranas is essentially of order coherence lengths in superconductors. I don't know how to make it much tighter than that.
Numerical solutions to a much lesser size than the coherence.
So what is the scale? Okay. So it could be smaller, but I don't know by what factor. Any other questions? Okay. Oh.
Is it true that this slide is still 5 years old?
Do you mean that the proposal is 5 years old, or well, this part is from 2010 or so?
The breaking news in the friendship book of all of them. Comes down to graphene.
Where did I put that? Oh yes. Well, 5 years might be an exaggeration. Okay, breaking. I have a slow time response, so it's not exactly break anymore. But yeah. Thank you for pointing that out, Mark.